Welcome to Chapter 7, titled Energy and Energy Transfer. In this chapter, as well as the next, we'll explore another method for solving problems that may be too difficult to solve just simply using Newton's laws. We'll use the energy approach. Every physical process that occurs involves energy and the transfer of energy. To use this approach, we first need to define the system. The system can be made up of a single object or several objects. It may even be a region of space, such as the Earth, for example, so that our region is isolated from the rest of the universe. But before we begin to explore energy and energy transfer, which in physics is called work, we introduce yet one more force which was not studied before in chapters 5, 6, or 13. This is because this force, known as the spring force, is a variable force and depends on position. So let's begin by introducing the spring force. Our system, in this case, will be made up of a spring connected to a block of mass m. The spring force, sometimes referred to as the spring restoring force, behaves in a manner known as Hooke's law. Therefore, we say Hooke's law describes the spring force F sub s and its relation to the displacement of a spring. First, we can see that F sub s is equal to a negative constant known as the spring constant times displacement of the spring. So let's see how this diagram illustrates the spring force. In this case, the block of mass m attached to the spring has been pulled to the right by some applied force. The spring force or restoring force tries to restore the spring to its equilibrium position, and you see points in the direction which is opposite the displacement of the spring, hence the negative sign in front of the spring force. Once the spring reaches the equilibrium position so that it has no displacement from its equilibrium, the spring force is zero since there is no restoration which is necessary. If, on the other hand, the applied force had pushed the spring to compress it, the restoring force, the spring force, would point in the opposite direction to the displacement. Once again, the negative sign. So we say that K is the spring constant with the unit of Newton per meter, because of course the spring force itself is in the units of Newton. And so this is an N, which I'm having a little trouble drawing. And so the spring force is a measure of the stiffness of the spring, how the spring is likely to restore itself to its equilibrium position. The negative sign, again, is due to the fact that the spring force is always in the direction opposite the direction of the spring's displacement. Here is an animation of Hooke's law. In this case, we see that for some value, mid-range value of the spring constant, we are going to pull the spring to the right and observe how the restoring force changes direction according to whether the spring has overshot its equilibrium position or is compressed below its equilibrium position. And we can see that the value of the force ranges from maximum to the right in the positive direction to minimum in the negative direction. If we adjust the spring constant to make it much stiffer, we can see that this time the force is much greater. Likewise, if we reduce the value of the spring constant, we can see that the force is much weaker. So, we consider the spring force as well as the applied force, which plays a role here because the applied force is what precipitates the spring force into action. And we stay within the realm that the applied force is relatively small for this approximation to be correct, so that the applied force is always taken to be in the positive direction, or rather in the direction of the displacement, and the spring force is always activated to oppose the actual displacement. Now, what if the applied force is so strong that it exceeds what is known as the elastic limit of the spring? In other words, the spring before stretching, the spring as it's approaching the elastic limit, exceeding the elastic limit and breaking beyond. In other words, if we consider a graph of Hooke's law, where the applied force is on the vertical, the displacement is along the horizontal, we can see that Hooke's law is valid up to the elastic limit, beyond which the spring will not longer be able to restore back to its original shape. And in fact, if the applied force exceeds even that plastic region, we get the breaking point. Well, now we're ready to talk about energy. And we'll do this by introducing the term work. You may recall work is the transfer of energy. And the work done by a constant force is the energy that a force delivers to an object as the object is displaced over a certain displacement delta r. We will also consider what happens when the force that does work, in other words, that transfers energy to the object, is a varying force. In other words, a force that varies over the displacement, such as the spring force. We begin with the work done by a constant force. The term work we write out as W-O-R-K so that there is no confusion possibly with the word weight, for example, or any other term in physics that may be abbreviated by the letter W. Work is defined as the scalar product of the force acting on an object as the object undergoes a displacement delta r. If you recall, way back from when we studied vectors in chapter 3, we covered a very small section of chapter 7 introducing us to this type of vector multiplication. It yields a scalar, and so when force as a vector is multiplied in this fashion with delta r, the displacement vector, the definition of scalar product is magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the object's displacement. Scalar quantity, therefore, can be positive or negative. And in fact, what we'll see is that the transfer of energy that occurs can sometimes be positive, i.e., an object gains energy, or the transfer of energy can be negative, i.e., the object loses energy. So, if friction is the force that is doing the work on our object, kinetic friction, as a matter of fact, specifically, our object or system loses energy and slows down. If, on the other hand, the force of gravity is doing work on the object might either have a positive amount of work done on it or a negative amount of work done in it, depending on the direction of the displacement of the object relative to the force of gravity. Now we know the force of gravity is always downward, so if the object is being displaced upward, the angle between delta R and F is 180, so gravity will do negative work, our object will slow down. If on the other hand our object is being displaced downward, in other words along the same direction as the force of gravity, the angle is 0, and so we say that the force of gravity does positive work on our object. Our object gains energy. Let's view an animation.
A person pushes a box along a horizontal surface. Because a net force is applied to a mass and the mass moves a net distance, we say that work has been done. The work done depends on the angle between the force F and the displacement vector S. Because the person pushes the box at a diagonal, only part of the force vector actually contributes to the work. If the box is pushed so that the force is parallel to the direction of travel, then all of the applied force does work. When the person pushes the box at a diagonal, the component of force that does work is F cosine theta, where theta is the angle between the force and displacement vectors. Forces that are perpendicular to an object's displacement do no work on the object. The work done is the component of force along the displacement vector times the distance moved.
So in other words, in this short video, S is delta R, F is the force that she applies, theta is the angle which the force that she applies makes with the horizontal, which by the way is parallel to the direction of the displacement. So what we have to do here is that we have to consider that only the component of the force, F cosine theta, which is parallel to the displacement, contributes F cosine theta times delta R, contributes to the transfer of energy that the box gains. How about work done by a force that varies over the displacement? In this case, we consider delta x's very short segments of displacement multiplied by the component which is along the direction of the displacement, and here our example is along the x direction. And if we shrink delta x down to very small displacements, in the limit that this occurs, we have an infinite sum. We have an integral. An integral is the sum of very many displacements of minute length dx. So when we take the integral of f along the direction of dx from the initial object's position to the final object's position for which the force was acting on the object, you can see that we can obtain the same value that we would obtain through integration by if, for example, we know the curve of f along x, f versus x. We break up the curve into rectangles, each of length delta x and of height fx, and in the limit that delta x becomes dx, then we can basically just sum the area under the curve fx bounded by the x-axis, and so by obtaining this area we are effectively obtaining the value of the integral. So in other words, if we can readily obtain the area under the curve f bounded by x, it is entirely equivalent to taking the integral of f dx. Let's view a video animation of work done by a variable force.
A box slides down a hill, pulled by the constant force of gravity. In this case, the displacement changes direction. To determine the work done, we need calculus. We break the path into infinitesimal parts. The infinitesimal amount of work expended in moving the box along an infinitesimal path, ds, is f dot ds. To find the total work done, we must integrate all of the little bits of work done along the total path. This is the general definition of work, which applies no matter how f might vary during the motion of the object.
So you can see here that regardless of the form of f, if we can obtain the area under a graph, it's entirely equivalent to solving the integral of f dot ds, which again, we don't use ds. In this case, ds would be just one component dx, and the component of force along the direction is what we are integrating. So let's go ahead and integrate the work done by the spring force as the spring is stretched or compressed, in other words, undergoing a displacement in the x direction. In this case, work done by the spring force from initial to final, and initial might be the equilibrium position, the final might be the stretched or compressed distance. We've got the spring force, negative kx, dx, the infinitesimal displacement. When we perform this integral, we get minus a half k, parentheses, x final squared minus x initial squared. Rearrange the terms in the parentheses, we get the work done by the spring force, negative 1 half kx final squared minus 1 half kx initial squared. If we now consider the work done by the applied force, we have the applied force kx along the direction of displacement dx, integrate the terms, and we see the work done by the applied force is just the opposite in sign as the work done by the spring force. So we might say that when the applied force does work on the spring technically has a gain in energy. When the spring force does work on the spring loses energy. Let's view an animation of the spring force doing work.
Work must be done to compress a spring. The hand supplies the force that drives the glider into the spring. To overcome the spring force, the hand must apply a force kx. The spring pushes back with an equal and opposite force minus kx. The work done by each is the area under their respective force curves, which is equal to half the area of the rectangle kx by x, or 1 half kx squared. Since the displacement is in the same direction as the force applied by the hand does positive work on the glider. Force and displacement are in opposite directions for the spring, and so the spring does negative work on the glider. Note that the net work done on the glider is 0.
In this case, because both the spring and the applied force are doing work on the spring. We conclude the first part of Chapter 7. In the next part, we'll study two forms of energy which are very important: kinetic energy, or energy associated with motion, and gravitational or elastic potential energy, energy which is stored as a result of a force doing work on an object. Until then.